Good morning. We are delighted that you can join us. I'm Al Romick, Executive Officer of the National Academy of Engineering and member of the NAE Aerospace section. In partnership with the American Institute of Aeronautics and Astronautics, we are pleased today to present the Yvonne C. Brill Lectureship in Aerospace Engineering. For this virtual lectureship, all of the registrants will be muted. The lecture will be recorded and made available on both the NAE and AIAA websites. First, let me take a few minutes to tell you about Yvonne Brill. She was a pioneering rocket engineer. She was elected as an AIAA Honorary Fellow in 2008 and an NAE member in 1987. She was a trailblazer at the time when women were discouraged from entering the science and technology fields. She embraced the spirit of AIAA and NAE. While Yvonne shaped the future of aerospace through her work propulsion systems, she did so much more. She served as an active voice for women in our profession, helping ignite an understanding that one's gender has no bearing on one's ability. Yvonne Brill embodied NAE and AIAA's commitment to stay at the cutting edge of new thinking. Her expertise and ingenuity not only revolutionized how satellites traveled through the heavens, but she helped revolutionize how our profession viewed its members. The lectureship emphasizes research and engineering issues regarding space travel and exploration. It also addresses aerospace education for students and the public, as well as ensuring a diverse and robust engineering community. The lectureship was established in 2013 in memory of Yvonne. The event is hosted every other year in conjunction with the NAE annual meeting. I would like to thank everyone who took the time and made the effort to submit nominations. I would also like to thank the Brill Lecture Committee, chaired by John Cassani. With that, over to you, John.
Thanks, Al. Before we begin this lecture, please allow me to introduce the awardee, Miguel San Martin. Miguel is from Argentina. He was born on his family farm in northern Patagonia. He grew up in Buenos Aires and as a youngster followed closely the Viking and Apollo programs. Because of this, he expressed a keen interest in working for NASA. Because of this interest, he went to a technical school in Buenos Aires called the Don Bosco Industrial School, Pius IX, where he could study electricity and math. After graduating, his father said to him, "If you really want to work for NASA, you have to go to the United States to pursue your university studies and your dream of working for NASA." So Miguel did that, much to his mother's great sorrow. Miguel came to the US and applied to Syracuse University. Speaking no English, he was given a bye in the SATs for English, but nailed the math and technical sections. He was admitted and he learned English and graduated summa cum laude with a degree in electrical engineering and was named the Engineering Student of the Year at Syracuse. He received his master's degree from Massachusetts Institute of Technology. The degree was in aeronautics engineering, aeronautics engineering with a specialization in guidance, navigation, and control, or GN&C as we say, for interplanetary trajectories. After graduation, he was hired by the Jet Propulsion Laboratory, that NASA center that specializes in interplanetary space exploration. Early in his career, he worked on the Magellan mission to Venus and the Cassini mission to Saturn. He was later named chief engineer for the GN&C system for several highly successful lander missions. The Pathfinder mission, which landed Sojourner, the first rover on the surface of Mars, and then the same role for the roving vehicle Spirit and Opportunity on Mars in Mars 2004, and most recently, the Mars Science Laboratory, which successfully landed a 1-ton rover on Mars, that was on, I think, August of 2012. Miguel was a co-architect of the Curiosity's innovative SkyCrane landing architecture and also served as the deputy chief for entry, descent, and landing. San Martin has served as a panel consultant for many space missions, including TOPEX, Mars Pathfinder, Mars Polar Lander, Deep Impact, and Phoenix. Miguel is a JPL Fellow and a member of the National Academy of Engineering. There will be a question and answer session after the lecture. where you can submit questions. Please do so during the lecture rather than waiting till the end. So now it is my distinct pleasure to introduce to you the recipient of the 2020 Yvonne Brill Lecture Award in Aerospace Engineering, Miguel San Martin. Miguel?
Thanks, John. It's an honor to be introduced by you and having you as a friend. And I'd like to also thank the American Institute of Aeronautics and Astronautics and the National Academy of Engineering for this award and for the opportunity to tell the work we do at JPL and NASA on landing on Mars and other places. So, my presentation is about the evolution of guided navigation and control systems in the problem of entry, descent, and landing. So I think that not everybody might be totally up to date with those terms, so I'm going to define them first very quickly. Entry, descent, and landing for missions that need to land a package of scientific instruments on a planetary body like Mars. In particular, entry, descent, and landing applies to planetary bodies with an atmosphere, okay? We call entry, descent, and landing that process of slowing down, coming from cruise phase of the mission, and in case of Mars, arriving at velocities of 20,000 kilometers an hour, and touching the upper edges of the atmosphere, 125 kilometers of altitude, and then going through a process of slowing down, first using the drag of the capsule as it enters the atmosphere, then opening a parachute, and finally some sort of retro-rocket engines to softly, or as you see, not so softly, land on the surface. And so we call this process sometimes the 7 minutes of terror. And the reason for that name is simply because it's the highest risk of the mission when we do this landing. And the risk is brought up by many factors. And one of them is simply uncertainty in the planetary body where are we going to land. In particular, in the case of an atmospheric body like Mars, where we use the atmosphere to slow down, any uncertainties in the winds or the density of that atmosphere introduces risk to our landing. And then when we touch down, obviously we touch down on terrain that is also uncertain, okay? And our landing spacecraft had to be able to survive different slopes and rocks distributions that Mars can throw at us. So that's the risk of the environment that the planet has at that point for us. In particular, it's riskier when the first time that we land on a planet or in a new world, because interestingly, you will need to land first to be able to know how to design the spacecraft. Unfortunately, we cannot do that. There's a chicken and the egg problem. So there's always a little bit higher risk the first time we do it. And then we are learning more and more from the surface missions. And also it's risky because the spacecraft go through all sorts of changes and getting rid of heat shields, opening parachutes, and all of that complex dance of mechanical dance and software and guidance, navigation, and control systems. We cannot test it in its totality. So that's what makes the entry and the landing so challenging. So so now let's define what I mean by guidance, navigation, and control. Well, guidance, navigation, and control is like the cruise control in your car that maintains a certain velocity. In our case, guidance, navigation, and control controls the orientation and the translation of the spacecraft to achieve a certain goal. In this particular case, landing the spacecraft on the surface of the planet. And it consists of a set of sensors like inertial measurement units that detects the rotation and translation of the accelerations to the vehicle, a landing radar that measures the altitude and velocity. And you'll see later on, sometimes we have cameras where we use to navigate relative to the surface, okay? And then that sensor data is processed by algorithms and software in a computer, and then commands thrusters to actually affect change in the orientation and translation, so we can achieve that goal of landing softly or not as softly on another planet or another body. So that's what we call guidance, navigation, and control system. In particular, I'm going to talk about EDL when it comes to Mars landers. This is where I did most of my career, but it's also where we've done more experimentation with different systems, and starting with Viking and ending with Curiosity, and now Perseverance that is on its ways to Mars. And so you'll see, the mechanical systems differ drastically between different approaches, and the guidance, navigation, and control that goes with them it also changes accordingly. They are both need to be designed, the mechanical system of landing and the guidance, navigation, and control that goes with that needs to be designed simultaneously and to actually help each other into a robust system. So the first mission that landed successfully on Mars was the first attempt by the United States, was Viking I and II, was in 1976. This was a mission that it was really an Apollo spacecraft level for a robotic spacecraft. I mean, in today's dollars would be higher than $6 billion. It consisted of an orbiter and a lander, which first would get into orbit, and then the lander would separate, going through that dance that I showed you before, would actually land softly. This is in the family of soft landers. The vehicle it lands on the 3 legs. This mission, Viking, had to develop practically everything because it was the first time it was done. So the aeroshell, the parachute, the throttleable engines, these regulated engines that allows this vernier, very fine control of the spacecraft, and the landing radar, all of that stuff had to be designed from scratch. A lot of this technology till this day we use, like the parachute design and the aeroshell shape. So this mission was very exciting to me, and I follow it as a youngster, like John introduced before. It turns out that this mission, prior to landing, to take off, they went through a landing site selection, obviously, tried to, based on the images from previous orbiters, determine what is the safest place that this lander could land, okay? And they made a determination, they chose that landing site. They launched the Viking I, and the hope was to be able to land on the 4th of July to celebrate the 200th anniversary of the United States. Unfortunately, once they got into orbit, and now they examined the surface using better resolution cameras with the orbiter, they found out that this place that they had picked was actually not as safe as they thought. So they had to start a crash effort to find a new place to land, which they did, and they landed in the 20th, a few days later, July 20th, on the 7th anniversary of the lunar landers. So as I said before, I follow this very with great intention and expectations. I remember very well going to the town in the Patagonia, small town, to get the newspaper, and I saw this picture of the footpad of Viking lander on the surface, and this is when I decided that this is what I want to do for a living, and I was very fortunate that I was able to do that. So it was a great success. They take an image around, took several images, but one of them is particularly striking. This place that was supposed to be so safe to land has plenty of places that could have been in total disaster. Like, for example, that rock to the left that they call Big Joe. Just the lander, the Viking lander, was not designed to land on top of that. So they were very surprised that, because they actually thought from the reconnaissance that they did from orbit that they were actually landing in a better place than this. So in some ways they got lucky, but again, this is the first time they land, so there's always this uncertainty of the place you're going to for the first time. And so this is actually the effect of this rock, of Big Joe. It was something that would be lasting for all the future designs, because now we have to take it into account. So the next mission to land on Mars occurred 20 years, which was a perfect time for me to finish high school, go to college, and get myself hired by JPL. And it turns out that there were two challenges in this mission. First of all, this was a faster, cheaper, and better mission, which means we didn't have the budgets that Viking had, okay? And so we had to, and all these guidance, navigation, and control equipment, these sensors and thrusters, they're expensive, okay? So the project didn't have the money to pay for those things. And the other one is that we had to solve the problem of Big Joe. We had to be robust to big rocks, okay? So the solution was a mechanical solution. So a passive mechanical solution is just you wrap around the lander with airbags, and then which are, comparatively cheaper than all these complex electronics and software, and then also very robust to rock. So that is the theory. So and then you use a very, very rudimentary guidance, navigation, and control system. So one could say that Mars Pathfinder represents the evolution of GN&C in that sense, but that's fine because the architecture it was what it required. Okay, so and again, the Pathfinder consisted of a stationary platform and a separate rover Sojourner that flew with it to Mars, and it was deployed once we got there. So the landing sequence was the first part very similar to Viking, and as I said before, using similar aeroshells and parachutes. And then the idea was at a certain point to inflate that airbag, okay, and then and that would be it. Let the airbag bounce away. But it turns out that the terminal velocity on the parachute was still too high to be able to do that. So they needed to add the mechanical engineers and these retro rockets. They're very simple rockets, much simpler than the engines that Viking had. They are impulsive, so they are only a few seconds duration, 2-3 seconds, and you only need a very simple measurement. It's a radar altimeter. So all of a sudden, we have a little bit of GN&C creeping into the system, and that's how I got involved, okay, which was perfect for me. And then, so anyway, so then the system, at certain altitude, it computes the velocity and the altitude at a certain moment opens the parachute and fires the retro rocket. So the system comes at a standstill about 10 meters of altitude, when then we cut the bridle that connects it to the rest of the system, which flies away, and then the airbags bounce and bounce again. So what could be simpler than that? Well, it turns out, and I had to apologize because this is an MER, not a Pathfinder video, but it's a good, some poetic license. So this is a test of an airbag that takes place in this vacuum chamber in Plum Brook, part of Glenn Research Center. And you can see here, by the way, a gigantic hole that it took place. So it turns out that this very simple airbag system, it's not that simple when it comes to analyzing the dynamics of this vehicle entering in contact with rocks at certain velocities. And the rocks would be of all types of shapes, and the velocities could be also dispersed over a wide spectrum of velocities. Because remember, the idea was to use a very rudimentary GN&C system because the airbag could take all of this stuff. So it ended up being a very complicated problem. You could not model this in computers. So you had to resort to empirical, and some ways, I hope I don't offend my mechanical friends, a trial and error process to continue bouncing these airbags, and every time the hole appeared, come out with a solution, and sometimes consisting in changing the stitches or adding layers of material on top. And in one of the attempts of trying to desperately understand the physics, they created this acrylic rock with pieces of rocks, so then you can film the interaction of the airbags, which is pretty chaotic. And you can see that this was not a very good, favorable interaction. But in any case, they figure out all these problems and they solve them, and you cannot argue with success, but you could do say that the simplicity of the airbag in principle, it was exchanged by very complicated analysis of how this system interacts with an uncertain terrain at uncertain velocities. So anyway, it was a tremendous success. Here we have a picture of a Pathfinder on the surface of Mars, Ares Vallis, and you could see Sojourner before being deployed and some of the airbags. I like this picture too because it's Sojourner taking an imager of the Pathfinder station, and you could also see the airbags. And finally, we have here Sojourner now studying a rocket, I think what's called Yogi, and that was a tremendous success too, but because the scientists realized that mobility was such an important part for scientific exploration in a planetary body. So our future missions were tended to be rovers. So after Pathfinder, there was a couple of attempts, one at landing using more of a Viking approach, what's called Mars Polar Lander, and it did not work. And I will mention a little bit later again, that mission. But so then the next attempt was, we coming from 2 failures. So we go back to the surface of Mars with the Spirit and Opportunity rovers. But this time the idea was, well, first of all, let's use what worked the last time, and that was Pathfinder airbag system. Okay, so then we'll use that. But instead of having a stationary scientific lander and then a rover separately, let's just have a single rover. So now you could have a more capable rover. As you can see now in the middle, you have the rover all folded in this case, and they're protected by a tetrahedron. And then outside you have the airbags. Now, here is another situation that I didn't mention before. It's that this airbag system with a very simple guidance, navigation, and control system, which is not controlling only the vertical velocity, had an Achilles heel. And it came in the form of, if you get a gust of wind during the descent, when you fire those retro rockets, you might not be aligned with the vertical and with your vertical velocity, like you could see here on this picture to the right, in which case you will still do, because of the cosine effect, it's still favorable, you will still kill the vertical velocity, but in the process, you would actually induce a large horizontal velocity that could damage the airbags. So that was a big problem. We had that problem in Pathfinder. However, it was the risk posture was much higher, was part of faster, better, and cheaper. We were allowed to take more risks, and now we were coming from 2 failures. So our bosses tell us, you guys have to fix that. So, and we did. So what we did is we added more guidance, navigation, and control. So we added an inertial measurement unit in the back shell, this part of the aero shell that then we released the lander. And then we put these small little rockets called Transverse impulse rocket systems and a software algorithm on board that would determine if a gust of wind had disturbed the dynamics of the vehicle and started oscillating as a pendulum. And at the right moment, it will fire these little rockets to straighten the system and make sure that that is spent at equal amounts on both sides of the vertical. So the total velocity, horizontal velocity was reduced in this case. Now, this was not supposed to reduce it to 0, just to bring it down from a velocity that could destroy the airbags to one where the airbags could survive. But that was not all. We had another problem, which was even if you don't have a gust of wind, the whole column of air could be moving in steady state, in which case the IMU would not be the right sensor to detect that. For that, we needed a Doppler velocimeter like Viking had, but it turns out that we didn't have one handy, and also because they don't make them, it's a production item. So we had to come up with another solution. And we had a camera available still, of all the cameras that you need in a rover, and then we put it in the descent system such that we could take images, and by looking at how the features move through image to image, you could compute the horizontal velocity of the system. This came actually pretty late in the game, and but we did that. And we added the camera, and we added the software to compute this velocity. And also that fed into the tier system to have a complete system that handled both steady state winds and wind gusts. So as you can see, this system that originally in Pathfinder was supposed to be passive and airbag driven, all of a sudden we were adding more and more guidance, navigation, and control, but we still had a pretty hard impact with the airbag, because the GN&C just brought the velocities to within the airbag capability. So if you want to see how this system works in its entirety, I'm going to show you here this animation. This is actually an animation of the telemetry, a reenactment of the telemetry that we received from the vehicle after it landed, the Spirit landed, telemetry. And then, so we just took that telemetry and we reconstructed all the motions of the vehicle. This is a Spirit landing in Gusev crater. This place, our statistical analysis showed that there was a high probability of getting a gust of wind and maybe even an horizontal velocity. And as you can see later on, it just happened that. I mean, a lot of people felt that we were over-designing these things, that there will be no wind. But it turns out that, as you can see now, you're gonna get a gust of wind move to the right, and you're gonna see also a little flash to the that's the TR's rocket. And there we go, and we cut it. So the system activated, just like we expected it activated, and brought the velocity within the airbags. And you can see how in this system, the airbags, and by the way, these bounces are the reconstructions of the real bounces. And so you can see how the system lands and continues landing. So colleagues at JPL, said, when it's hard enough to land one time, and now an airbag landed lands multiple times. Every time that it lands, there's always a probability of having a rock that gives you a bad day. So, but in any case, again, I keep saying it, then opportunity came in later on, and 3 weeks later, and landed successfully. And here is the opportunity in Eagle Crater. In this case, the airbag bounce, and who were unknown, it landed inside a little crater called Eagle Crater, and you can actually see some of the impacts of the airbag, and then the system, not surprisingly, stopped kind of at the center of the of this crater, and another interesting thing here is that it landed right in front of a rock crop of sedimentary rocks. So the geologists were extremely happy with this situation. We cannot say that we did that intentionally. We were just lucky, but we are willing to take that. In any case, again, 3 out of 3 airbag landers worked. So these airbags ended up being very, very successful, but not necessarily as simple as we thought originally. And right after MER, well, actually while we were working MER, the mission Phoenix, which was essentially a copy of the same lander that had failed in 1999 after Pathfinder, they were successful in landing that one in the northern Arctic plains of Mars. Now, this lander, as you can see, is more of the style of Viking. It was built and designed by Lockheed Martin, the company that built Viking. And as you can see, and it was actually a low cost. So the interesting thing about this platform is that they figure out a way of actually having a guided navigation and control system in an economical, I don't want to say cheap, a mission, because actually they did manage to use thrusters that are used for another applications and use it in a pulse width modulation that brought all sorts of interesting engineering problems that were overcome. And then also the radar was based on a radar of a military aircraft. Therefore, they were able to have GN&C on a reasonably low price system, which is essentially what the airbag system was trying to do. So they went a different way, and they achieved success. And this platform also was used in InSight that landed last year. Now, neither one, I mean, InSight or Phoenix, as you can see, can solve the problem of Big Joe, right? They are not very tolerant to big rocks, but there are plenty of places to go on Mars the probabilities of finding rocks. And now we have the statistics, now we know about Mars, where to find those places, and then also being able to do scientifically relevant studies on those places. So this is another way of thinking about the problem. Can we make GN&C cheaper so then you can afford it in a mission? So then followed curiosity. So now the challenge is increasing here, because now we had to land vehicles of the size of a car, in this case, a Mini Cooper, and almost a ton of mass, of weight. So these present new challenges to the inter-descendant landing and the guided navigation and control system that goes with it. So the team, the inter-descendant landing team, started analyzing all sorts of possibilities. So the last thing that worked for us here at JPL was airbags. So let's look at airbags, right? So the idea was to surround the rover with airbags. I have to say personally, I had it with the airbags in all their complexities, and the idea of having a 1-ton rover bouncing for 2 kilometers, 5-story height, didn't seem very plausible to me, but it was probably doable. But so then we thought about, well, why don't you land this with legs, like Viking did? Well, the problem that, well, again, as we said before, legged landers are not very robust to rocks. And because the propulsion system is below you, okay, it keeps you pretty high up from the surface, okay, and that's a problem when you have to egress a 1-ton rover. So that created a very big problems with the egress of the rover. So so we thought about all sorts of systems, like pallet would be another system that essentially, instead of having legs, you land on a flat surface, but and you try to spread the propulsion system so then that step is not as high. But at the end, as most of you know, we settled for this thing we call the SkyCrane, which essentially it's like a helicopter, but instead of having a propeller on top, it has rocket engines, and the rover is being lowered on 3 bridles like a helicopter and directly on its wheels. So it totally solves the problem of the egress, because we land with the rover ready to go, which is very, very advantageous. But also has other interesting properties, because the engines are not below you, like in a Viking style lander, where the engines is interacting with the surface and creating all sorts of debris and carving holes that actually might destabilize the landing. Now the engines are on top, so that's not happening, okay? And therefore now you can actually take your time and slow the vehicle down as slow as you want to go. Well, in a legged lander, there's a minimum of velocity. You don't want to spend too much time landing because of all these interactions of the engine plumes. So, and the other advantage that you have, that these thrusters are canted, therefore all this debris is being generated away from the rover, and contamination too. And we kept learning other properties of this landing system. As you can see in this, actually this is a simulation that we are running the full system here and illustrating it, and landing the rover using the SkyCrane with a high slope terrain and full of rocks. Those artifacts there are supposed to be rocks. And you can see the SkyCrane allows you to deposit the rover slowly and don't drop it until the whole rover is supported by the surface of Mars. That's when we cut the bridles and we fly away. Okay, a legged lander in a situation like this, the moment that one pad touches the surface, you shut off the engine. So therefore, the vehicle is going to drop. Okay, and actually that could be destabilizing. You might actually not only damage the vehicle, or just you could turn it over with the legs upside up. And another interesting property that we learned about the SkyCrane is the touchdown detection. All soft landers needs to have a way of detecting when you arrived, okay? And usually you have switches in legs, like Viking and Phoenix did, and we need to be redundant, and it needs to be interrogated at a high frequency, because you want to shut off that engine the moment that one of the pads touches down. So that is complicated, but it would have been even more complicated to put all those sensors in wheels, right? They don't, these wheels were designed to rove around, not to touch down, to be touchdown detectors. So we thought about this other technique, like, we already have an inertia measurement unit that we're using to control the velocity of the vehicle. When the rover all of a sudden is being supported by Mars, those thrusters don't have to apply as much force to fight gravity. So essentially you can use the GN&C system like a big scale that you can measure the weight of the system below you, right? So then when the weight of the system actually drops the amount of a rover, you say, well, we landed because the rover is no longer there. And actually what you see here is that the actual signal of of the landing day of Curiosity, where you have the raw measure weight. Again, we actually created a measurement that is the weight of the system, and you can see how the weight is starting to go down below the rover weight. There's a transient there, and we actually filter that signal. So you can see here the filter signal crossing the threshold and then touch down. So it was a very, very robust system. Okay, the biggest problem that we had with the SkyCrane was we were convinced, engineers that understand control systems and mechanical engineers, that this system was a robust system, but we had to convince the decision makers, our bosses, okay, and they were very concerned that this pendulum dynamics would go unstable. So we had to do a lot of explaining to do, and one of the things that we used to draw is diagram like this, that the control system really behaved pretty much like a suspension in a car, where you have a spring and a dashpot, and that would essentially always take energy out of the system. In control system, we call that phase stabilization. And we created we did even a demonstration I want to show you right now. It really was a demo, it was not a test, also to illustrate the decision makers that the physics were actually simple. And so we did this, for example. So, all right,
set it up again.
So we did that demonstration. You know, none of that actually worked. I mean, at the end, the project manager, Pete Teisinger, decided to ask the Aerospace Corporation to get a panel of experts to review our idea and give us a thumbs up or a thumbs down. And in the panel of experts, we had even Jack Schmidt that worked on in Apollo 17, the last astronaut to walk on the moon. We have also an engineer from Apollo that designed and studied the landing gear of the lunar module. They were about the first one, the easiest one to convince them that we were not that crazy, but that's what it took for them to give us the thumbs up. And so very quickly now, I'm going to take you through this drawing where I have here the touchdown velocities of the different missions. The y-axis, the vertical axis, is the vertical velocity, and the horizontal axis, the horizontal velocity. So we start with Viking here at a very low touchdown velocity of 2.4 meters per second. Then we remove the GN&C system because now we ask the airbags to do more work. Originally, we were asking it to do too much, right? Because we didn't have the retro rocket. So then they decided to put the retro rockets and a radar. So we're doing a little bit of GN&C. That brings the vertical velocity down, but it created a horizontal velocity problem. Then we added tiers and dimes that I described before for MER and the Mars exploration rovers and Spirit Opportunity, and that brought the velocity lower, but still, you know, you needed an airbag, but it was within the airbag. So then when it comes Curiosity, we actually went full circle and we decided not only to do a soft lander, but do a ultra soft lander, if you wish, because we had to land on the wheels of the rovers. And by the way, there were no shock absorbers like you had in Viking. So we just landed on the wheels. They had to be designed to support that. So we went full circle, and that's what also the journey of GN&C. Another element that is important in these landing missions is the size of the landing ellipse, which is the area where you land. The smaller the landing ellipse, the more probability of finding a place that is safe and scientifically interesting. So here you could see different landing ellipses for different missions, starting with Viking and finishing with Curiosity, superimposed on top of Gale Crater, which was the destination for Curiosity, which consisted of a crater of 150 kilometers diameter with a mountain in the center. That's where the science was. And there was only this area between the border of the crater and the mountain to land that it was safe. So as you can see, none of these ellipses could do that. So we needed to reduce the ellipse to a size that would enable the choice of these scientifically interesting places. So the way we did that in Curiosity was by using a lifting entry as opposed to a ballistic entry, where the spacecraft center of mass is offset to produce a lift vector that we have here. So now with thrusters in the back, you can guide that lift vector, and a guidance navigation and control algorithm, you can navigate automatically, obviously, the vehicle to reduce the landing ellipse. And we use actually the Apollo algorithm to do this. And we worked in conjunction with our colleagues and friends at Johnson Space Center to do that development. It was a great success. We used it for the first time, and we landed 2 kilometers from the center of the ellipse. So that's another technique that is in our back pocket now. So this is a picture of Curiosity with Mount Sharp in the back. It was a big success. The SkyCrane worked, entry guidance worked. We proved that a complicated and expensive guidance navigation and control system has the advantage of now you can land a vehicle like rover like Curiosity very softly on its wheels. So on the other hand, I mean, we had to, it was true that in order to do that, we had to spend a considerable amount of money developing actuators like these thrusters, which was essentially, it was the Viking, we resurrected the Viking engines for this mission. And then we had to develop a landing radar from scratch. So the problem that we're having in this landing mission is that while certain components that we use, like computers and inertial measurement units, there is a market for them because they are used in orbital missions, you know, they're used by the DoD or science missions or communication satellites. There's actually there's no industry of landing in other bodies, so we don't have off-the-shelf radars and the right propulsion system to land, the navigation system and propulsion systems. So that's why every time that we build one of these missions to land somewhere, we had to build this from scratch, and because the parts are they are obsolete, and so it's very expensive. So that's the problem that we're still dealing, and between having more passive system like an airbag system or a more complex system like Curiosity. So so now towards the future, as I mentioned before, we have the Perseverance rover going to Mars on its way to Mars. It's going to arrive there February 18. And it's essentially, it's based on the same design as Curiosity, as far as the cruise and the entry, descent, and landing, and the rover, but obviously with scientific instruments much more capable, and also it's going to do something. It's going to take samples of Mars and it's going to encapsulate it for another mission to bring them to Earth. It's what we call Mars sample, the first leg of the Mars sample return mission program that is going to be very exciting, and NASA is working right now. As far as the EDL and guidance, navigation, and control, there are a couple of important innovations. The first one is a modification to the parachute deploy logic that allows us to a reduction of the landing ellipse even smaller. And as you can see here, we have an effect of almost 10 in area. The landing site they picked was Jezero crater, which and they put the ellipse right on top of this delta that was formed by the waters that were deposited by this river here on that crater that was a lake at that point. As you can see, that where they put the ellipse is extremely dangerous place because you have all the cliffs and rock formations associated with the delta. And the reason why we can get away with that, by the way, also that's where the best science is, because it's right inside the landing ellipse. The reason why we can do that, because of this new innovation, we call terrain relative navigation. In this system consists of a camera, just kind of like the cameras that we have for dimes, but this time we have a computer just dedicated for the computer vision intensive processing that is required. And what this system does is takes images, and then it has an onboard map of the landing site, such that by looking at features comparing the features in the images with the features in the map can reduce the uncertainty in its location from 3 kilometers to less than 50 meters. So essentially it's like a GPS that lets the spacecraft know, okay, I'm here, okay? Now the way that information is being used is because it has another map on board that catalogs all the hazardous areas. And essentially, so the vehicle, once it finds out where it is, it looks for the closest safe haven, the place that is not hazardous, and then it chooses to land on that place. And after that, it's pretty much similar, it's identical to MSL. So that's a very exciting technology that will be demonstrated in February 18, and we call it terrain relative navigation. So onwards to the future, it turns out that all these technologies that we've been developing in the Mars project that enhance Mars science, now we can project it to future missions. Like for example, we're talking about Europa, which is a moon of Jupiter that below a thick layer of ice, scientists believe there is a liquid ocean that actually might have life today. Okay, we're not talking about fossils, but actually extant life, which is very exciting. And it's even more exciting the fact that some of these water and biological and alleged biological products might actually go through the cracks of the ice to the surface. So a surface mission would be of extreme importance. We already have a mission right now being developed to essentially fly by over Europa multiple times to observe it. And, but this would be a surface mission. So now we can think about how do we use all these lessons learned from exploring Mars and all the toolkit that we developed for landing on Mars for a mission like this. So
We don't have any.
one issue that we have is, you know, again, like Viking had when they were designing their lander, is that we know a little about the surface, and the little we know are from Galileo pictures, and they are low resolution images. They tell us that the terrain is pretty rugged, okay, and so we had to design a system that can actually tolerate that. And we are, in parentheses, I forgot to mention this, we have technology money from NASA to develop these technologies. So we're gonna take some of those tools that we developed for Mars and adapt it. Like, for example, we talked about terrain relative navigation. In this case, we're gonna use terrain relative navigation to reduce the landing ellipse to the absolute minimum. So the idea is, you can see here in red is the area of landing that the vehicle will have without TRN. The little circles, it will be once we, you know, with TRN and the map would be developed from the information from Europa Clipper, which is being developed right now, then we will be able to determine and land the position and land within 200 meters. And you can see that while the larger ellipse is difficult to find a place on Europa that is flat, that looks like there are no features within that landing area. Once you reduce to 200 meters, you increase your chances of finding a place of great scientific interest and that is safe enough. But that's not good enough, because even for today on Mars, the orbital images, you can never see the type of terrain that you need to see at the scale of the lander itself, which is meter scale. So we are developing right now, again, with this technology money, this laser sensor that allows us to do a mapping of the surface and develop what we call it a DEM, of a digital elevation map. Okay, it's a 3D topographic representation of the surface, such that another software can look for the flattest area and have the spacecraft autonomously choose that area and land. And so then we're developing that technology, and which, by the way, we have not done that on Mars. So this would be an enhancement to our GN&C palette of technologies. And this is the type of technology, by the way, that is being developed for also for autonomous cars, but not necessarily the same instrument. And finally, there's a third innovation here that is actually is more of a mechanical one, but it's enabled by GN&C. Therefore, I'd like to mention. And as you can see, the idea will be to use also a SkyCrane technique on Europa, but in this case, the landing legs is not a rover. The landing legs are left to actually, while it's touching down, to float, to move freely. And then when the vehicle belly touches down, then we freeze the legs. And then and you can see if you do that, you can actually land on terrain that is very rough, just in case that all of the other prior techniques that I mentioned, TRN or the hazard detection sensor fails, you still want to have a lander capable of negotiating or surviving a very rough terrain. And so I'm going to show you here, this video maybe illustrates how, as we land, the legs contour with the surface. Again, without the precise landing that the SkyCrane and GN&C with the right sensing instruments allows, this will not be possible. And so we're building a life-size prototype of this type of system, and I'm going to show you, this is just the last things to show, a video of how this would work. Europa is an airless body, therefore it doesn't have an atmosphere, and therefore instead of calling EDL, we call it DDL, the orbit descent and landing. So we are using a solid rocket motor there to slow down, as opposed to heat shields and parachutes. And then once it gets closer to the ground, we'll go SkyCrane, and there you'll see some of the testing that we've been doing with this landing gear. Well, I think that you got the picture, but essentially it adds robustness to the system. We have multiple layers of where GN&C systems and mechanical systems work together to allow you to have the highest probability of success when you go and visit a place that you never visited before. So I'm now at a point that I can make some conclusions and then go to questions and answers. So I hope I have shown that through the years, the advances in guidance, navigation, and control has enabled visiting places that are scientifically interesting but challenging, and doing that with ever more complicated instruments, rovers and landers. So that's what's done, and based on the tools that we have developed in doing that, now we can look into the future and start designing missions to other new worlds that where we haven't been before, but now we are in a much better position that Viking was back in the 70s when the toolkit was smaller. So we have a much bigger toolkit based on advanced GN&C systems. And in particular, I'd like to also mention Titan, where NASA has approved a New Frontiers mission called Dragonfly that's going to be very exciting and also uses extensively guidance, navigation, and control system, complex ones. And you already mentioned about Europa, how we are working and hoping that will become a mission soon. So however, the bad news is that there's still perceived risks and concerns about the cost of this complex guidance, navigation, and control system that makes them difficult to adopt in competed, the NASA, competed missions like New Frontiers and Discovery. I've been on that side where you essentially you're encouraged to prove that you don't need it, and unfortunately sometimes you do need it, right? So then you end up with a system in order to sell it through and go through a competitive procurement system process that perhaps it's a little bit less robust, like you will have built it if these instruments if you are able to design it with a more complex guidance, navigation, and control systems, right? So, but again, the problem is that these instruments are expensive because there are not enough of an activity to develop them. So I want to leave on a positive note, and I'm going to say this is my opinion, perhaps my wishful thinking, perhaps, is that the new efforts by NASA now to go back to the moon, to the surface of the moon, first with robotic spacecraft and then with humans, is going to develop an infrastructure of landing GN&C components that is going to make using those components for exploration of other parts of the solar system more viable. And we won't have to have this difficult choice between cost and what's the most robust way to land on another unknown world. Okay, so that's it with my presentation. Thank you very much. Sorry that I overstepped my time a little bit. So, John?
Well, Miguel, thank you for a really most interesting lecture. Before we proceed with the Q&A session, I'd like to present you with your certificate for this honor. This being a virtual presentation, your presentation was virtual. My presentation of the certificate to you will also be virtual. You and I are in separate rooms at JPL at the moment. The certificate is at NASA headquarters. I mean, at the National Academy of Engineering headquarters. But so for now, we have to make this a virtual presentation. So I'll turn to my right where you are. You can turn to your left, and I will hand you a virtual certificate.
Thank you. Hey, John. Thank you very much.
Okay, so now let's look to the question and answer. There's a couple of interesting ones. The first one was very simple to answer, I think, for you. Is why is a parachute needed when there's no air in space? I think you want to take a crack at that pretty quickly.
Yeah, well, there is air on Mars. I mean, there's a tenuous atmosphere compared to Earth, but it is good enough. It's 1% of the atmospheric density of Earth, but it still helped us a lot slow down the vehicle. Actually, more than 99% of the energy that we bring we actually get rid of it through interaction with the atmosphere, first with the capsule and then with the parachute. So there is an atmosphere, there is air on Mars.
Yeah. Okay, I think the simple answer is there's no air in space, but there is air immediately around Mars. Mars has an atmosphere.
That's right.
It is very useful for taking out a large fraction of the velocity, the approach velocity that the spacecraft has as it bears down on Mars. It has to be reduced to zero. And the parachute doesn't do it all, but it does. It makes a large contribution. The next question is guidance active for entry and descent phases? And the second part of it is, how big is the landing dispersion ellipse? I think you talked about that, but is guidance active during entry and descent?
Well, so guidance is, we have guidance of the entry, descent, and landing. We have guidance in the entry and in the, and the final phases of landing. So during the entry, when we're still the capsule, I mentioned before, the lifted body allows us to do entry guidance, essentially, using the Apollo algorithm to reduce the landing ellipse. The landing ellipse, it gets shrunk between, from hundreds of kilometers to tens of kilometers, actually less than 10 kilometers these days. And then when in the parachute, there's no guidance. We just let the wind push us in the direction that it wants to push us. And then back when we get rid of the parachute and go into propulsive flight, we have relative guidance in the sense that the terrain relative navigation, in the case of Perseverance, is going to say there is a safe place to land. And then after that, it guides this vehicle to land in that safe place. So of the three phases, we have guidance in two phases, not in the parachute.
Yeah, I think you gave one of your charts was very interesting. You showed the air ellipse for Pathfinder and for a number of succeeding missions, each one showing smaller and smaller landing ellipses. Can you just quantitatively describe how large the ellipse landing ellipse?
I can go back because my memory.
Curiosity.
So, for example, Curiosity, and forgive the English units. I mean, it's pretty much 12. The longest the semi-major axis was 93 kilometers. And Curiosity, we were, 93 miles. We went to 12 miles.
Okay,
and,
my eyes aren't good enough to read the number for the 212 Curiosity ellipse. What is the magnitude of that?
It was about 7 kilometers by 20 kilometers.
And what kind of improvement do you expect on the Mars 2020? On the
Mars 2020, we expect reduce the ellipse from MSL was 25 kilometers by 20, which, by the way, we did better than that. We did 25 by 7 kilometers to 7 kilometers diameter landing ellipse.
Okay, thank you. Would you, here's an interesting question. Can you give an example or two of the technologies developed for these missions that have found commercial application on Earth? And I guess I would start off by saying there are military applications, obviously, in terms of delivering, military target weapons to, or what have you, to targets. But what we're doing here, I think, really is developing technologies that will allow some future entrepreneur, business person like Elon Musk or Jeff Bezos to take those technologies and augment them and develop a profit-based business that could exploit those technologies. But what about commercial applications? Other than that, are there any that you can think of or that you know about that you could mention?
No, I don't know any. I think that, John, that you explained it very well. I think that's the hope is that these techniques, right? And now with going back to the moon, the idea is actually to create an economic infrastructure that it will be self-sustaining. So it's always hard to tell when we're doing these missions for science, and in the process we develop these technologies, and then they get applied to other things. but it's always surprising how the final uses, and I don't, to be honest, I don't keep track of them. I only can say that if you don't do anything, nothing's going to happen. But if we are restless and curious and we explore and we develop things, there's always a chance that these things are going to be used for other applications that we've never dreamed of. And exactly which ones I could not tell you at this time.
Okay, just a second. This is back again. Here's an interesting question. You know, given your background and your remarkable move from Argentina to the United States, the question is, what do you have any specific advice that you would give to international graduate students that want to pursue a career at NASA? That's basically the footpath that you followed. But have you got any specific advice or general advice to others like that who might want to follow in your footsteps?
Well, I always advise them to do at least a graduate level degree in the United States, in a United States university, because that allows you to connect yourself. First of all, learn about the system, and connect yourself with the industry or the area with the experts in the area of your interest, and that would make it easier to solve a major problem that we have that when it comes to the United States from other countries, which is the immigration issue. Is not always an easy one, and it's very difficult to unless you are a renowned scientist, that go directly from let's say from Argentina to a university in the United States or to some research lab in the United States. If you come, before you build a career, it's very difficult to do that immigration jump without going through the American university system. So that's what I recommend. It's not a guarantee either, but it makes it. It gives you a lot of time to also to make those contacts and to impress people, right? Because once they find through your college work and letters of recommendation from professors, then people will be willing to do the paperwork to get the immigration problem solved.
Here's one you might scratch your head about a little. I don't know if you have any insight, but are the GN&C systems used by Japan, China, Russia, India of similar design to those you described, or what can you say about that?
Well, there are not that many landers that are being built, but I think that the Europeans that they attempted on Mars, unfortunately unsuccessful so far, they are very similar. I mean, they are similar principles, similar sensors and actuators. And China, the laws of physics dictates there are not too many ways of doing these things. And also, we publish papers and they read them. So you don't see major differences. Here, the thing that separates, perhaps the success or the failure is all the processes and all the machinery that we've been developing during years to make sure that we eliminate all the mistakes of the systems. But again, we all study from the same books, and so there are no major differences, and there are maybe different preferences, but I would say that it's very similar when there are landers.
So the next question is kind of interesting. With the success of the SkyCrane system, do you think we'll ever see airbag landing system used again?
That's a very good question. Again, there is the issue of cost, right? And so yes, and we actually, I've sat in more than one meeting, proposals where I said, well, what if we use a simple, airbag landing system? And so yes, I think that it's for certain type of applications, you could use an airbag, and actually for certain type of applications, you can use legged landers, right? And we are going to. I mean, that's very likely that that part of the sample retrieval lander, which is part of the Mars sample return mission, could be a legged lander. So all of these different architectures have their place, right? And so we haven't totally eliminated any of them. And actually we keep discovering new ones. So that's a good thing.
Yeah, I got one interesting question that's coming from Patagonia. It's, congratulations on the award from Grau Roca, Patagonia.
Okay.
Also, how do you think rovers will evolve design-wise, and how will that affect GN&C in terms of wheels, configurations, etc.?
Well, that's an excellent question. Our original rovers, you know, they were the same way that we talked about, you know, guidance, navigation, and control systems are evolving on the entry, descent, and landing system. Guidance, navigation, and control is also evolving on our rovers. So we already had, for example, visual odometry, we call it, these techniques of using images to navigate the rover. So we started using that in MER, and then we continue with Curiosity. Now they are for Perseverance, they are taking the same computer vision system that is being used for the landing terrain relative navigation. Now they are using the same box to process the images from the Perseverance rover to do, you know, essentially visual odometry and navigation of the rover at a much faster rate than Curiosity. Curiosity had to take images and had to wait to analyze the images, and not only did it for visual odometry, which is measuring how much you're moving, but also did it to find clear paths of terrain for the vehicle to autonomously navigate. And you had to wait because you had to do it in the main processor, which was not very powerful. Now, with this very powerful computer vision engine, it's going to be able to speed up that. And also that in Perseverance, and I'm not part of the Perseverance project, or in particular the surface part of the Perseverance project, so I cannot give you much detail, but they are implementing more automation of all the processes that in moving the robotic arm and placing it on a rock and taking a sample. So so everything is becoming more evolved, and we are using more GN&C even in the surface.
There's a very interesting question here, but it may be above your pay grade to answer, but I think it's just worth mentioning. The statement is, with Ingenuity, that's the Mars 2020 rover, Ingenuity being flown on Mars, and underwater rovers proposed for Europa. The question is, landing small spacecraft such as Ingenuity on planetary bodies without large rovers worth the cost? Do you have a reaction to that?
Well, Ingenuity is the helicopter, right, that we're carrying on the rover Perseverance. That is going to be an experiment, an exciting one for the first time, right? We're going to fly a helicopter on Mars. Also, by the way, it also has very sophisticated GN&C. Not just, first of all, to control the helicopter itself is not an easy thing to do in an atmosphere that is very different than Earth. So the engineers have to figure out all the dynamics of helicopters on the atmosphere of Mars, but also it has computer vision operating, you know, to navigate the helicopter. Now, yes, I mean, you have to send a helicopter or you know, where there is an atmosphere. Titan is one, and that's where the APL mission, NASA's APL mission, Dragonfly, is going to use a quadrotor, but it's going to be a big one, just kind of like Curiosity size, but instead of propellers, instead of engines, it has propellers like a quadrotor, and with a lot of GN&C. So again, depends on the application, you will have different platforms. And we also looking to also send more capable, the helicopter Ingenuity for in Perseverance is going to be a test to see if that technology works. But we are already anticipating that it's a success, looking to see how would you do a whole mission around them for Mars. So we are working on that.
Okay. Let's see. Here's a short question. Why are wheels better than tracks?
Well, that's a good question. I don't know. I'm not a mechanical engineer to answer that question. And the only thing I've been told that is the wheels are simple enough and efficient enough for what we need to do. I mean, people are talking about walking type, you know, like the quadrupedal, I guess, rovers. That could be a future thing. But it's my understanding is when I asked this question to my mechanical engineer friends, is that from an energy point of view, wheels are optimal for exploration, and that's what we've seen so far.
So I got another compliment from Argentina. It says, great presentation here from Buenos Aires. What is today the main impediment to sending humans to Mars? And if I may, I'd like to provide the answer to that, because it's
Please.
you could get into a long discussion on that. But I think very simply, the short answer is the main impediment to sending people to Mars is the requirement to return them to Earth. That certainly established the requirement on the Apollo program, and that is the main impediment. I don't know if we'll ever get around that. Other than that, the main impediment is going to continue to be the cost and the expense of providing a means to return them as well as get them there. Let's see, how are we doing on time? Can somebody help me with that? Until I get an answer, Miguel. Another interesting question. Could you use some kind of steerable parachute, perhaps not as a paraglider, but similarly as ballistic steering, by pulling the parachute strings to further reduce the landing uncertainty ellipse? That's an interesting question. Has that been looked at?
Yes, excellent question. And we looked at it and it was not very promising. Again, I mean, the atmosphere of Mars is so thin that you pretty much, the glide ratio, which is the thing that you will need to actually get big distances. At least the last time we looked into it, it wasn't there. So there was all this complexity for a very small control authority. I mean, you have some control authority, but not enough to be worth the complexity of trying to add all these steering devices, which, by the way, it also creates risk that the parachute doesn't open. So, and it's very expensive, by the way, to develop these parachutes, because you have to really test it in Martian conditions. So, and we have enough problems as it is today with the parachutes, simple parachutes that we have today. So, but we looked into it, and the conclusion at that point was not enough benefit for the cost.
Okay, here's an interesting one. In terrain relative navigation, how effective is it to compare images or magnified images, i.e. features, from an onboard map? Are matching features guaranteed? In other words, the question is, you're taking an image of a terrain, and you're using that, comparing it to what you think that terrain is. How likely is that you'll get good matchups in that situation? Well,
I mean, our system, our terrain relative navigation experts, engineers, my good friend Andrew Johnson has been working on this for many, many years, and they actually have flown this system in helicopters on terrain here on Earth that approximates the terrain on Mars, and they have tried to stress the system by varying the first of all by varying the different surfaces, places that are kind of bland, not that many features, or other ones that have a lot of features, and different characteristics of terrain, but also different illumination, because there is a mismatch between the illumination of when you created the map and then the illumination of when you land. That also makes the algorithm is supposed to recognize where you are be a little bit more fragile. But we they tested this under all conditions, and it looks really, really robust. Otherwise, we would not have bet a mission of the cost and the importance of perseverance in such a technology. So we feel that we have a very, very robust system here.
Okay, here's another question. I think it's also from Buenos Aires. Great lecture. What will the surface dust blowback from the landing thrusters interfere with the visual sensors for TRN on Europa, for example?
Well, so yes, the answer is absolutely yes. Therefore, we try to finish using all the sensors the non-inertial sensors, that whether you're using a Doppler radar or you're using cameras, we try to stop using them about 50 meters or above, depending on where you're going, where we know for sure that up to that altitude, the effect of dust, of dust being disturbed and by the engines is negligible. And then after that, we go with the inertial measurement unit, which doesn't need, to have clear fields of view. So that's our strategy. So, but it is a problem because you would like to continue making your measurements all the way to touchdown just to reduce your errors. But the possibility, even if it doesn't happen, just the possibility of having that dust makes us want to quit while we are ahead and then go inertially after that.
Okay, thank you, Miguel. I think it's time for us to wrap up. Unfortunately, we've still got a lot of, there's still more interesting questions, but we just don't have the time to pursue it. And I thank you for a great presentation. And I'd like to remind the listeners that the next Brill Award will be 2 years from now. And I hope that all of you will be able or see fit to rejoin us at that time. So thank you very much.